This is Math 1127, Introduction to Statistics. This session is about approximating binomial distribution using normal distribution. Now, in the past session, we talked about both binomial distribution, which is the probability of a particular number of success out of a series of identical trials. Now, that process is a little bit more difficult compared to normal distribution, which is basically the bell curve shape, and you use normal CDF, you use the Z table to figure out the answer. Normal distribution is a far easier and simpler tactic compared to the binomial. So the question is there a way to mimic or try to get an estimation of a binomial distribution using normal distribution? And it turns out the answer is yes. You just have to meet a few of the credentials. So in order to use normal distribution to estimate binomial distribution, you have to check to see if the binomial distribution is normal enough. Meaning, does the sample size, and the probability at least mimic a little bit of the bell curve shape? So how do we know that? You need to check to see the following conditions. One, so remember that for n, so remember binomial distribution, you have n, right? What's n? N is the number of trials, and p is the success rate. So I would say this: the mean of success has to be larger than 10. So what do they mean by that? The mean is n times p. It's the number of trial times the success rate. So if you have 10 students, and I say the success rate in general is 60%, well then 10 times 60% is 6, right? So on average, 6 people should pass. So n times p must be bigger than 10. Number 2, the mean of failure has to be larger than 10. Actually, make it like this. So, well, what are we talking about here? Well, here, n times 1 minus p. What's 1 minus p? Some people will say 1 minus p equals to q, and that's just failure rate. It doesn't really matter. Let's say success rate is 60%, right? What's 1 minus 60%? Or 100% minus 60%? That's 40%, right? Well, the chances of failure would be 40%. So that is all it is. So the average of that also has to be bigger than 10. In order for you, so basically, let me see, both of these conditions have to be met before you can use the normal distribution. Now let's look at some examples. So for number 1, let me move this down here. Number 1, consider the probability that no less than 71 out of 303 people have been in a car accident. So let me just type something up here. So we know that for this problem, n equals 303. All right, and we also know, I'm going to make this lowercase, and we also know that no less than 7, so there'll be for x would be less, it would be no less than 71. There'll be x greater than or equal to 71. So the game is this, right? We need to see if we're going to use this as a normal distribution. We have to check whether or not this thing is going to fit the normal distribution. I know the question is not asking for that, but it's probably good just to do it anyway. So in for this problem, right, is let me see, let me write something down here. So let me show you this particular trick here. So if you have in a binomial distribution, because it is discrete, we have to turn it into a continuous variable. And you're like, what do we mean by that? Well, remember, right? Let's say you're talking about students, right? Let's say we got 10 students. You cannot have 5.5 student passing because binomial distribution is discrete. It's either 1, 2, more than 3. You cannot have 3.5. So we have to turn this somehow into a continuous variable. So if you're talking about the probability, right? For example, the probability of exactly, say, 3 successes will be considered the probability of success of 2.5 to 3.5 successes. Basically, we take the 2.5 to 3.5 probability and just mash that together into 3. So, for example, right? Example 1. If I have binomial probability of x equals 3, right? I can write this down. Then that's probability of 2.5 less than x less than 3.5. I basically have to give it a range. So that on your normal distribution, you can use this. Example 2. Probability of x, let's say, equals to, how about this? X, how about less than, let me use this symbol here. Less than or equal to, say, 3. Right. Then that will be equal to probability. Right. So I should say this is binomial. How about it? Binomial probability. This is normal probability. So it makes a little bit more sense here. Normal. Right. And this will be x less than or equal to, now think about this, right? You are including 3, less than or equal to 3, right? So you have to make sure 3 is in the conversation. So that would be 3.5. Because you are taking 3.5 with you, that's incorporated into 3. However, example 3, if I say binomial of p x just less than 3, now what's up? If it's just less than 3, well, then you have to make sure 3 is out of the conversation. So if 3 is outside the conversation, that will be x less than. Actually, you don't. For this, you can just say less than. The reason it doesn't really matter because normal distribution, that 1 point doesn't really mean anything. So this will be less than 2.5, like that. So if 3 is not in the conversation, you have to start from 2.5 and below. Right? So same thing if I say binomial say P x greater than or equal to 3. Then you have normal probability of x bigger than 2.5. Why is that? Because you're now considering not just 3, but the range is 2.5 to 3.5. So you have to go from 2.5 and above. Then the last example, of course, is 5. Binomial P of x greater than 3, right? Strictly greater. So if it's just greater than, you have to say x bigger than 3.5, right? Because you're not including anybody in 3. So these guys and these guys should help you. Right? So now let's go down here and see. We have to consider the probability, right? Where n equals 303. X is bigger than or equal to 31. So that's like this. There's like the binomial probability of x greater than 71, or greater than or equal to 71. I wish there's a hard key for this. 71 equals, well, what does that mean? In normal distribution, there will be probability of x bigger, right, straightly bigger than, remember 71 means you're going to start out at 70.5, like that. Because 71 in normal distribution means 70.5 to 71.5. So you got to take from 70.5 since you have to include 71. So there will be area to the right of 70.5. That will be A. That's the answer, right? Now what about this one? Consider probability that exactly 62 of 503 will not vote. So let's see. So this is the probability, the binomial. So the binomial probability of x equals exactly 62. So that's equal to, let's say, normal distribution, right? Probability. Well, if it's exactly 62, then you're talking about from 61.5, between 61.5 and 62.5, right? Because it's equal to that, right? Like this. So there will be the area in between those two. Like that. Okay. So not too bad, right? You just got to think about any one individual number. You have to take the range for 0.5 before and 0.5 after. So now let's look at this, number 3. Consider the probability that more than 38 out of 100 houses will lose power. And assume that the success rate, right, the losing power rate is 3%. Can we use binomial probability, or can we use normal distribution, right, to approximate this guy? Well, the conditions are, you have 2 things. AMP must be bigger than 10. Yeah, I don't like this. AMP must be bigger than 10. And 1 minus P must be bigger than 10. So let's check, right? AMP in our case equals to, so maybe I should say this. N in our case equals to 100. What is P in our case equals, they say the success rate is what, 3%, right? So 0.03, like that. So NP is 100 times 0.03, which is equal to 3, right? That's less than 10. So right off the bat, fail. So that's a no. Basically, your number is not big enough. Your number has to be bigger. Your success, the mean of your success has to be big enough for you to use normal distribution. So that's not going to work. So let's try this one. So this one says n equals, okay, 114. And the success rate equals 0.25. So let's see what is NP. NP in our case is 114 times 0.25, which is equal to, what is that? 20, so 26? Yep. Actually, probably, that's more than the whole. Can do math right now. 114 times 0.25. 28.5, my bad. 28.5. So that is indeed bigger than 10. So, yes. So this one is so check, I guess. Check. What is n times 1 minus p now? That will be equal to 114 times the probability of 1 minus 0.25. So the failure rate. So in our case would be 114 times the probability would be 0.75. That's the failure rate. So that's equal to, let's see, 4 times this. So that's 85.5. And that is bigger than 10 again. Check. So since they're both yes, then yes, it is appropriate to use the normal curve to approximate this distribution. Basically, your number is big enough on both sides, on the success side and the failure side, for you to use the normal distribution. And now for number 5, let's check this out. So first, we have to consider, should we use the normal curve first, right? So let's say, actually let me move this down. So in our case, n times p is like this. N times p is going to be 100. Right, got stuck right here for a second. 158 times what's the success rate? 0.13. Right. So because that's the n, right? Maybe I should type it up and not be lazy here. N equals 5 and 158, and the success rate is 0.13. There you go. So now let's say this right. We've got this is equal to 158 times 0.13, which is 20.54. That's bigger than 10. So check. Let's try p times 1 minus p. So that'd be 158 times, and 1 minus 0.13 would be 0.87. So let's say this, and that is bigger than 10. So check. So we should, right? So we can use normal curve to approximate this binomial distribution. So now the question is, how do we do it? First, we need to find the mean and the standard deviation. So this normal distribution will have mean equals, will have the same mean and standard deviation as the above binomial distribution. So first, let me give you the formula for those two things, right? So we already did the mean. The mean is the mean of a binomial distribution is n times p. Right? Easy, right? Which is what we've been doing, right? The standard deviation of a normal of a binomial distribution is, this one's a little bit tricky, so let me get this formula going. It's gonna be, let me use this is a symbol for standard deviation, right? Equals the square root, what's the radical? The radical, right, of n times p times 1 minus p. Can also be weird. That's with this one. Let me just make it look a little bit more official right here. Because the mean of a distribution of a population mean is always this, right? Equals n times p. So use these two formulas to get the mean and standard deviation. So in our case, right, the mean, right, is gonna be n. So maybe I use this right here just to make sure the mu equals n times p equals, it's gonna be 158 times with the data. I know we did it already, but I just wanna make it official, right? Times 0.13, right, which is equal to 20.54. Just like that. Standard deviation is going to be this. Equals the radical of np 1 minus p, like this, equals the radical of 158 times 0.13 times parameter 1 minus 0.13, which of course is 0.87, right? So maybe I might as well just go and copy this. Just like this. Okay. So that should equal to, let's use a calculator for this. The radical parameter 158 times 0.13 times 0.87, and I have 4.2273. I used to do 4 decimal places. So there you go. We have the standard deviation and the mean. So how does that help us, right? Well, for this normal distribution, if I want to know if the binomial probability is, what is it, fewer than 12, so that's x less than 12, right, like this, that will be equal to the normal distribution probability, right, with x less than, remember, we are taking away 12 altogether. 12 in normal distribution is 11.5 to 12.5. So it has to be less than 11.5. So how do we do this? Well, isn't that equal to normal CDF? Remember from the last session? Less than, so normal CDF, what's the left bound? Will be negative 999,999, right? Negative infinity. How far do we go? 11.5, because we're doing less than 11.5, right? So then that would be the mean of let me see, 20.54, right? That's up here, right? That's the mean, right? And then what's the standard deviation? 4.2273, like this. It's pretty weird, right? So let's go ahead and check it out. That would be second for normal CDF, right? Negative 999999, and that will be 11.5, 20.54, and 4.2273. Done. So the answer is equal to 0.016. So in other words, that is 1.6% chances that you have less than 12 houses losing power out of 158, given the probability of losing power is 13%. So, and it makes sense the number is so small because, think about this, right? If the average is 20.5, so that means on average you have about 21 people losing power within a year, once a year. Then 12 would be a lot smaller than this, right? And standard deviation is 4.2, so it's a very rare occurrence, is what I'm saying. If the question here would be like a 20, right? Then that's a different story. So this makes sense. So let's try another one. So this time we're going to try to do a little bit faster instead of typing up everything. So number 6, consider the probability that greater than 94 out of 151 cell phone calls will not be disconnected. Well, here's the deal. We need to figure it out with this probability, right? So n times p, right? In our case would be 151 times 0.62. So let's say that would be bigger than 5. And that's 93.62. Of course it's bigger than 10, right? Check. N times 1 minus p, right, would be 151 times, that would be 0.38, right, equals 57. So that is also bigger than 10. Check. So that means we are clear to use normal distribution. So then the question is, of course, where's my mouse? So how are we supposed to do it? Well, first, we want to know what is the binomial probability of greater than 94. So x is bigger than 94. Like this. But then in normal distribution, right? Normal distribution, that would be the probability of x bigger. So remember, you are taking away 94. You're strictly bigger than 94. So that'll be 94.5. That's where you start. Right. So wouldn't that be so we got to do the normal distribution using this, right? So we already know the mean, right? The mean, right, we already did it, which is n times p equals 93.62. So now what's the standard deviation? The standard deviation should be the radical, right? So let me just do, should be the radical of 151 times, that was the times button, the dot right here, times 0.62 times 0.38. So let's see what that equals to. The radical of 151 times 0.62 times 0.38. So I have 5.9645. So let's see. This is going to be normal CDF And we are looking at the left bound. What is the left bound? The left will be 94.5 because we are greater than 94.5. So you got to start from there. We're going to infinity with this one. What's the mean? It's going to be 93.62. And the standard deviation will be 5.9645. Just like this. And then let's put this in the calculator. Clear this. Second file. Oh. Normal CDF. 94.5, comma. 999,999. 93.62. 5.9645. And I have equal 0.4414. In other words, 44%, about 44% of the times, you will have more than 94 out of 151 phone calls that will not be disconnected, given the probability of 62%. So, very nice. Right. So let's see. Let's do these as well. But I want to kind of skip out that these two. I'm just gonna say it. They are gonna work. So when you so for example, right, 146 times 57. So of course it's gonna be bigger than 10, right? And then the failure rate is gonna be bigger than 10. Same thing over here. So they are all gonna work. You can check if you want to, but we can use a normal curve. So now the question: what's the mean? Right. So the mean is 146 times 0.57. So that should be 83.22. What's the standard deviation? That would be the radical. I'm just going to put it in the calculator. 146 times 0.57 times 0.43. That's 1 minus 0.57, right? The failure rate. The standard deviation is this. I'm going to put in the decimal here. So what is the gain? We want to know at least 91. At least 91. At least 91 means really not for normal distribution, right? X bigger than 90.5 because you are including 91. So there'll be X bigger than 90.5 since that's the range. So there'll be normal CDF and there'll be 90.5 is the left. 999,999 will be the right. And then the mean is 83.22. Standard deviation is 5.982. Just like this. So let's see. I have 0.1118. And that's that. Now for the last problem here, let me just say this. We want to know the probability of exactly. So probability of exactly 91. So in other words, probability of x equals 91. Then of course in normal distribution, you will have to consider 91 will be in between 90.5 and 91.5, right? Like this. So that would be, so you just got to find the mean and the standard deviation, right? So let me say the mean would be 152 times 0.6. And that will equal to, what's that? 91 0.2. The standard deviation would be 152 times 0.6 times 0.4. And that would be a good old 6.0398, which is 6.04, right? That's good enough. So that's normal, CDF, 90.5, 91.5. The mean is 91.2, and standard deviation 6.04. So let's try that. Ninety point five, 91.5, 91.2, 6.04, and I got a 0.0659, and that's the answer. So 6% chance, basically 6.59%, and that concludes the session of approximating binomial distribution using normal